and thank you for being here today with us for this special webinar, because it's actually the last Great to Excel webinar, the last one of a series of 10 webinars we have been organizing during the project lifespan. So today we will talk about WAAM, of course, and topology optimization, and how the combination of these two technologies has the potential to transform drastically industrial design practices and allow the creation of complex and high performance products. But before we dig into the topic, as always, I will just present very briefly the Great to Excel project. So Great to Excel is a European project funded through Horizon 2020. Its objective is to demonstrate the potential of WAAM, wire arc additive manufacturing, for large engineering structures. Great to Excel brings together 21 partners along the value chain of wire arc additive manufacturing, including technology developers, material producers, WAAM manufacturers, and end users from different industrial sectors, as well as a certification body to accelerate the industrial uptake of this technology. Since 2020, the project partners have been working together to deliver 8 demonstrators for 7 industrial sectors. So here you have an overview of those demonstrators. For instance, there is a boat propeller for maritime sector. There is a holding ring for hydroelectric plant for the energy sector. We have also manufactured injection molds for the automotive and aerospace sector. So now we are reaching actually the end of the project. Great to Excel will finish in August, and now you can see how the demonstrator looks like in real life. So this is just an overview. And here, this is the project workflow, which is divided into 8 work packages. And today's presentation will mainly focus on the works conducted within work package 1 on functional grading and work package 2 process developments. Now I'm very pleased to introduce our 2 speakers for today, Constantinos and Franz, who are partners of the Great to Excel consortium. So Constantinos is actually one of the initiators of Great to Excel. Constantinos is an assistant professor at the University of Twente, also a scientific advisor at RAMLAB with a partner of the project. His research focuses on multi-material additive manufacturing. He's teaching material science, 3D printing, and materials and manufacturing processes. And he holds a doctorate in material science and engineering from Delft University of Technology, and has 10 years of international experience in research, both in academia and industry. Constantinos is a member of the Technical Committee on Additive Manufacturing of the International Institute of Welding, and he has co-authored multiple studies in material science and additive manufacturing. And Franz Bormann, our second speaker for today, is a research engineer and program manager at the Materials Innovation Institute, M2I, in the Netherlands. Franz has over a decade of experience in computational mechanics. As a research engineer, he specializes in performing finite element simulations to predict the behavior of components and structures, with expertise in fracture mechanics, dislocation mechanics, thermomechanical analysis, and topology optimization, which is a topic of today. His recent focus involves leveraging finite element methods and topology optimization for thermomechanical load cases for generating advanced product designs for additive manufacturing. So I will now leave the floor to Constantinos for the first presentation. Feel free to leave your questions in the chat and we will take them after the presentation.
Great. Thank you, Lucy, for the introduction. Welcome everybody to this webinar. My presentation will be more introductory to one Franz is going to address later. So for the people that are not so familiar with what we are doing with WAAM and on public request, we would like to give the opportunity to industrial and academic partners to know what WAAM is and what we can offer with this solution. So this project has been quite a journey from the early days, exploring the potential of multi-material large-scale printing and to seeing what the potential is for WAAM, and also by printing all the demonstrators that Lucy has presented in her introduction. We have learned a lot of approaches that need to be considered and a lot of elements that need to be addressed while working with traditional industrial sectors and their product designers, and also with the process engineers and welding engineers during the manufacturing stage, but very importantly also during certification after the parts have been printed. So I would like to start with a presentation on the technology of WAAM, and then Franz will focus on the combination of WAAM with topology optimization and all what we see is worth it. So today I am talking on behalf of RAMLAB, and this is something that all this presentation has to do with the approach that RAMLAB had throughout this project and what aspects of WAAM can be further improved. So if you have no experience with WAAM before and you're wishing to produce large components, where do we start and how do we make this happen? So WAAM stands for Wire Arc Additive Manufacturing. It is a technology that addresses large-scale metal components. Primarily, I would say components that benefit from this technology are of sizes larger than 0.5 meter. So we are talking about really large. For other sizes below that, I would say that other technologies have been developed in the last decade that proves to have more advantages. But the direct energy deposition family in general is the one that is of interest here. So we have laser metal deposition if you use a laser heat source, or electron beam additive manufacturing if you use an electron beam. But in our case, we use a welding arc, and that's why the technology is called wire arc additive manufacturing. So in the particular case, we combine the method of gas metal arc welding with a multi-axis motion system, and that's something that can be implemented either with a robotic arm or a gantry system, depending on the requirements of the user. So why WAAM is a good choice is that it is inexpensive compared to other methods because it uses standard industrial hardware and welding consumables. It is a high-speed method. We can reach deposition speeds up to 5 kilos per hour per robot that we have commissioned. That's something that has been developed quite substantially in this project, and we are able to demonstrate this also in a variety of materials. And by now we know that high-quality builds are achievable and far superior sometimes than conventional manufacturing processes. We are at the stage in the project now where end users are testing their products, and we are very happy to receive very positive input from them and feedback from the use in real cases. So it's something that high quality that is something that we stand for, and we are able to prove it in real applications. So WAAM is generally cheaper than its rivals. That's mainly because the gas metal arc welding is a technology that is very well established. Of course, complicated gas metal arc welding setups are giving significant benefits in part quality and in productivity, but also with simpler setups you can get decent results. Standard commercially available components are used to assemble a WAAM system. Of course, that also can be customized in case a specific user has special requirements. And the technologies are widely used and proven in industry. This helps with acceptance of the parts that are being produced. And what is of very high interest in our case is that multi-material parts can be printed because we can optimize in that way the performance of the part and also minimize the costs of the parts produced. I would like to add here that we can also see significant benefits in remanufacturing or in repair, and that is because we can customize chemical compositions locally in order to achieve higher performance in specific requirements in, for example, high temperature mechanical properties or wear. This production process is very scalable and it can take place locally even at remote locations. So if you can imagine that you can have locations where significant engineering talent is difficult to source, but they are important for manufacturing. A machine could be placed there and an engineer remotely can control the machine and produce parts in that way. And finally, the obtained properties that we see, that we say that with great confidence after so many years of research and development, that the properties that we are getting are generally superior to casting. And we can say with confidence that also from a defect point of view, the material properties are quite superior. So for WAAM applications, there are very diverse industry sectors: maritime, aerospace, automotive, oil and gas, and so forth and so forth. You can see here how many industries we can address. We see also lately that automotive industry is also taking this technology up for making actual parts, but also tooling. And if you want to define a good WAAM application, is, as I mentioned before, a large size metal part, a part that has long lead time, a part that has a custom design, a part that has a one-off or small batch production, and very demanding performance requirements. So demanding performance requirements is a good case because normally these cases also have stringent monitoring procedures. And in order to qualify a certain part, you need significant data input to be submitted for the qualification. And that's something that wire arc additive manufacturing can inherently produce. So the WAAM system involves a motion system, a gas metal arc welding torch, and a source. We commonly advise an external axis manipulator if you would like to have complicated geometries, but also a welding table can work with parts that have no overhanging angles. So it means that you don't have to print in the air, but things that are straight up or doesn't have overhanging angles can be printed on a table. Shielding gas is important because gas metal arc welding requires that. You need metal plate substrates and clamps for distortion. It could be plates or anything else that helps print your geometry. For example, Lucy showed you before the ring demonstrator that we had. In that case, it was not a plate, it was a ring as substrate. We also worked with tubular substrates or with other custom geometries that help manipulate our component. Then you need the toolpath simulation and generation software and CAD software to design the part. So regarding the software, I will cover here general software that is available. Of course, there are custom solutions by different WAAM system manufacturers. But here, RAMLAB specifically uses Autodesk PowerMill and PowerShape for their CAD modeling and toolpath design. But you can also use Rhino or Grasshopper or RoboDK that are also widely available. So per technology, you can also find specific software. So that's not what I cover here. Of course, proprietary software can also give a very good outcome, but judging from the widely available software, you can also create toolpaths quite concisely using these. What you see here is a workflow. We have how you make a CAD model and how do you create toolpaths with it. So you see that the toolpaths are created and are for different kinds of occasions. So you can see different kinds of parts that can be printed. So this is a 2.5D part, it's straight up. You see here we have overhang angles. You see here that you have geometries that are based on a cylinder and you can add features, or you can have non-uniform surfaces, or here again, cylinders that need to be cladded, or multi-axis toolpaths. And for complicated geometries, power shape can be used. So for a complete WAAM system, one would require to have a multi-sensor processing and control system. This is available nowadays by different suppliers, but here we feature the system of RAMLAB. The system of RAMLAB has a thermal monitoring, a geometrical monitoring, and also a process monitoring module. So you can see that you can also include further non-destructive testing modules. This in this project was developed in collaboration with CEA from France, and we included and we validated different methods for non-destructive testing. Certain features are currently available also together with the RAMLAB system, but also as standalone control systems. We have external cooling also being an option. So together with Air Products in our work package for process development, we developed a cryogenic cooling apparatus that uses liquid nitrogen to accelerate the prints, and we got very, very good results in increase of productivity. So we saw that a big loss in productivity in WAAM is when you deposit a certain layer, then you have to wait for a long time until you reach a certain temperature that is not too hot for a material to be subsequently deposited. And we saw that we could practically print continuously, even on parts that you had to wait, let's say, 5 minutes until you put the next layer. So it practically shortens the production time of a component to a minimum. The systems are also available in portable and flexible manufacturing modules, which is beneficial for repair and for workshops that deal with multiple types of parts. And post-processing and heat treatment are available on request, of course, because you can have grinding as a necessity or a heat treatment to relieve stresses or to optimize microstructure. For materials, everything practically as a guideline is that everything that can be welded can also be printed, of course, with some grain of salt there. But a wide range of materials has been already tested and validated, not only by this project, but also with various research and commercial initiatives. And now we have a very good understanding as industry on what can be achieved with this technology. We have demonstrated in the past as well that we get beneficial microstructures by using these. And this is a monomaterial example from a couple of years ago, but it's a very good indication of what can be achieved with WAAM compared to casting. And you can see here an example of bronze alloy. These are common alloys that used in industry for maritime purposes or energy purposes. And we see that a casting microstructure on the left has large grains and a lot of precipitates that were found to be detrimental, both for mechanical and corrosion properties. And these are actually absent in the right-hand side, where you see a finer microstructure and only this darker phase being present. The darker phase is what gives to this alloy its strength. And you see that in the left-hand side, you have very large islands of this darker phase, while here you have a greater dispersion of it. And this gives a better response in the mechanical properties, as you can see over here on the right-hand side. So current challenges, even after a very large European project, we still see that standardization of WAAM is not yet fully developed. We have produced a lot of outputs, and we will also issue a guideline at the end of this project, but we still see that it's application and sector dependent. Fully autonomous production needs to be achieved. So we have an autonomous system developed, but of course it has its limitations based on the testing that we have done up to now. So it is possible at this moment to produce a component just by giving a CAD design and a specific requirement, and then you get something out of it for certain materials and certain applications. But some boundary conditions still need to be manually controlled. So the materials need to be extensively tested in service. So this technology is present for the last decade maybe, but we still need to see these parts performing for their expected lifetime to see if anything unexpected occurs later. But fundamentally speaking, there's nothing to fear at this moment. Another point where we see lacking is that operators, welding engineers, and designers need to be trained for WAAM, and that's where Franz is going to make a big point in his presentation later. And we see that traditional engineering education and modern requirements in terms of advanced manufacturing don't necessarily line up. And there is a certain initiative in the higher education and also in technical education to introduce certain modules in that direction. And we try to stress that the industrial demonstrators that we make, they will promote eventually the use of WAAM as a viable production and repair solution. And specifically for this project, multi-material cases are in focus. Still, the design space has not been fully explored. We see certain attempts going out of the box, and topology optimization really helps in this. So designs that have not been attempted before because it was not possible, now they are. But at this point, industry needs also to accept that alternative solutions are possible. So that's what I would like to talk about today. And if there are any questions, I would be very happy to respond to them.
Thank you very much, Constantinos, for this very complete overview of the current developments of WAAM. So if there are any questions, you can just write in the chat. And if there are no questions, we can go ahead with Franz.
All right. Let me share the presentation that I can start already. Oh, that's the right one. There we go. All right. Well, welcome everybody. I want to give you now my presentation during this webinar, and my presentation is titled Beyond Intuition, Elevating Additive Manufacturing with Topology Optimization. But first of all, let me start off with a general introduction of M2I. So my company, who are we actually? What we do is, or who we are the bridge, or we build the bridge that over the gap between university research, academic research, and also industrial application. Too often it happens that we have academic research that are ending up in the trash bin because nobody is doing anything with that one. So in order to then facilitate the bridge towards the industrial applications, we also look at what is needed from industrial side, and we try to support that one. Then we further look also at industrial problems, where is actually a real need in society and in industry that are materials related. And with that one, we work then together with university in order to facilitate the answers towards those questions. Located, we are in Delft, as you see here on the right side on the map. Let me get the quick pointer, will be useful also later on. So they're in Delft. And yeah, we work mainly in national projects on a national scale, but also such as Grade2XL on an international scale. And we learn from that one a lot, and especially how important the cross-country collaborations can be. Now, to talk about what is actually, what Constantinos talked earlier about, the benefits of additive manufacturing. So we can produce parts with complex geometries. We can produce parts that are optimized with a strength-to-weight ratio, but also problem-specific parts, such as certain loads at specific locations, temperature differences in different parts, and so on. We can also look into, or we can also print multi-material solutions. And also one of the main benefits of additive manufacturing is reduced waste during the production. You don't have to mill anything away after the final product, and also the reduced costs. Now, the link with topology optimization here is that we can also design complex or create complex and non-intuitive designs that wouldn't be possible with conventional approaches. We can also design based on the specific application. What are the needs of the application, incorporated in the topology optimization approach, and get the respective designs. Furthermore, we can look for the performance, as again, this is in connection with the application-specific design. What is the performance we want to optimize for? And that's what we include in the topology optimization approach. We can also look at multi-material designs. We can look at the material and cost effectiveness of the designs. And what is very interesting is that with the topology optimization, you can also incorporate additive manufacturing constraints. Now, I'm talking here about topology optimization in my talk, but for those who don't know yet, or who are still not completely sure what topology optimization is, I've illustrated that one here in a rough schematic. So what you do with topology optimization, it is mainly based on finite element method. So what you do is, in the beginning, you set up your model, your CAD model, then you build your FEM mesh around that one. You give it the material properties, you set up all the boundary conditions, load conditions, and then you run the first FEM analysis. Based on the results that you get, the topology optimization routine updates the material distribution. So it removes material from areas that are not contributing to the objective function. The objective function is then related, let's say, the performance, strength to stiffness ratio, for example. And it also adds material at places. The topology optimization routine adds material to places where you actually need the material in order to enhance the performance. Then at the end, there's the convergence check. Is the convergence criterion that you have set for the topology optimization routine, is it satisfied or not? That can be either a certain volume ratio has been achieved, or volume fraction, so a certain amount of material has been removed, or it can be also that the performance has increased or has increased over the iterations sufficiently and does not increase much anymore, so that we can say this has been optimized. So if there's no convergence criterion fulfilled yet, it will iterate. The whole topology optimization routine will iterate until finally the convergence check has been achieved or has been fulfilled. And then we can say we have an optimized design. And that optimized design will then be prepared for additive manufacturing. So that's in a nutshell topology optimization. Now, imagine you want to perform a topology optimization, but you have never done that one yet. You don't know, you're not necessarily the FEM expert, but even if you're the FEM expert, you have not used topology optimization in the beginning. Then with the Grade2XL project, I learned a lot of industrial relevant challenges. I learned through the whole project many aspects that are important for successful topology optimization. And we have created, based on that one, also some guidelines that I would like to share now with you, such that in the beginning, you have a certain problem, let's say this part here, that was actually one of the demonstrators within our project. And you want to end up actually as a happy person with a fully optimized design. And that is, this design was created throughout the project based on the initial design that we had here. In order to get there, you just follow a few steps. And as everything in life, step by step, you're getting there. And if you want to make the big jump, it's always harder than you think. Now, what the messages that I want to convey here in my presentation are actually mainly two messages. The one message is to divert from the conventional design approaches. You might be smart as a designer, but in the end, if the algorithm is able to come up with a non-intuitive design, that's even more powerful. And still, as a designer, you can use that non-intuitive design as an inspiration to optimize it even further. So there is this kind of cross-section between the topology optimization routine takes away a lot of work for you, whereas then also it contributes you towards making your work more efficient. The second part I want you to take away with is to collaborate. So as a topology optimization expert, FEM expert, you need to collaborate with the designer, with the end user, with the additive manufacturing expert. Those are the most important things. And that's how you can then also create optimized design, truly optimized designs. Now let's start with the first part here. Step one, let's start with step 0 actually. So by the way, on the top right, you see the steps here, and you will see as we progress through the whole presentation that we get step by step closer to the happy person in the end. But the prerequisites, well, if you want to perform a topology optimization, well, you need software that is able to perform topology optimization. Since this topology optimization is based on FEM software, you also need FEM software underlying. And also in the end, you need to have CAD modeling abilities. So this all can be either incorporated in commercially available software, but you can also have that in-house. So there are two different approaches that you can follow here. Which one is recommended? I leave the choice up to you, to the end user. But those are the main requirements that you need for performing the topology optimization and arriving at the optimized designs. Now then the first step is for the topology optimization. You need to analyze the problem. So take, for example, the mold that we have here. That is a mold for winglets. That was one of the demonstrators in the Grade2XL project, and one that also Lucy earlier mentioned. And when we look at that one, what are the geometrical constraints? The geometrical constraints are clearly the internal surface for mold. So that needs to stay the same constant throughout the whole design process. Then you have heating channels. How are the heating channels? Here in this case, this one is straight, but maybe they are conformal. So following the surface area here. And the second one with this one is also you want to close the whole mold. So you need also clamping for the mold. Those are the geometrical constraints, and you need to be aware of them. And that one you need to also discuss closely with the end user. He knows what he wants, so you need to incorporate that one in the design. The second part is then the operational conditions. So for example, we have here a pressure and temperature profile over a certain amount of time. How does it change? Where are the relevant points that you need to include? Do you need to simulate everything in your FEM simulation and topology optimization? Or is it enough to take the most extreme points? Again, discuss it with the end user. So then further with the mold, when you talk about temperature applications with the heating holes, don't forget about the convection via the external surface. Makes the whole problem more complex, but also complexity is needed in order to have accurate results. Don't forget about that one. And the last part here is the material database. So you need to know what your material properties are. If you want to simulate or create a design for a specific application or range of temperature, such as we have seen here on the right-hand side, where we have a temperature profile for the application, a temperature curve for the over time, then you need to also have material properties as a function of temperature. Otherwise, you can simulate things, but is the design that you come up with in the end, is it the correct one? That's another question. So be sure that you have as many material properties as you can get. Now, the second step that I want to talk about is the model preparation. First of all, you need to set up the CAD model. So the very core of the problem. So here, for example, you see the first initial CAD model of the mold, of the winglet mold that I had. But then again, this is not enough. What I then did is to extrude the top and the bottom surface in order to allow a larger design space for the topology optimization, so that the topology optimization routine can decide to take material away or not to take it away. So I used Abacus for this project, and there it could not add material in places where there was no material present in the beginning. So I had to include the material on the top and the bottom. The second one is then the FE model. The very important thing for that one is to use a sufficiently small mesh size. If you have a sufficiently small mesh size, means you can also capture very intrinsic and small details. There again, it's important to collaborate with the additive manufacturing expert. He knows what are the smallest printable features. If you want to include them, then you need to choose the mesh size accordingly, even smaller or bigger, around the same size. If you choose smaller, you might end up with features that do not make sense. If you end up with, if you choose a mesh size that is bigger, it does not make sense either. You end up with features that are too coarse, and you might miss on the small beneficial details in your design. Very important also, FE model, as always, set the boundary conditions, even if it's just to prevent rigid body motion, and also then apply the operational loads. So in this case, apply pressure to the internal surface, apply temperature through the heating holes, and also don't forget the convection. Now, then with the next one, the preliminary analysis. This can be also a paper study, but also in this case, I did a numerical study. When we looked at the case, shall we print it monomaterial as a single material, or shall we print it as a multi-material solution? That was a very initial question in our project, and the answer got clear quite soon. So when I ran those simulations, I realized that the stress distribution, they are quite high. The stresses are quite high at the transition layers between material 1 to material 2 if you choose the multi-material solution. In this case, it was in the range of 500 megapascal, and this was way above the yield limit, and that's not a viable solution. So that's why we decided for the monomaterial solution. This one is, you can already do that way before step 1 and step 2. You can do a paper study, just have defined a very simple mechanical torque problem, where you then by hand calculate the stress distribution in material 1 or material 2. For example, having 2 bars, having 2 plates that are glued together. How is then the stress distribution as a function of the temperature? And yeah, exactly what I mentioned here. There were high thermomechanical stresses at those points here. Now, the fourth step in our little ladder or in our staircase is the setup of the topology optimization routine. For the topology optimization routine, we start with the design constraints. So when we have the beginning, the whole mold that we want to optimize here, then we need to know which parts of that mold should not be changed, should not be altered, such as the internal surface, such as the heating holes, such as the front and the back plate to prevent you need to close the mold. Those are the parts that should not be altered, and that's how that of the parts that you should set frozen. The remaining part of that one is the design domain. That is the domain where then material is being removed. Then the next part is, what is the optimization approach? What do we want to achieve with a topology optimization? We can set the design constraints, we can set anything else, but if we do not choose an optimization approach, there is no optimization in the topology optimization. What do we want to optimize for? So one of the initial ideas was to minimize the displacement along the internal surface so that the finally produced part does not change in its displacement versus throughout the whole temperature cycle. Now, although the benefit is there that this option is commercially available, it is not ideal for a whole surface. Either with Abacus or with commercial software, you're limited to a certain number of degrees of freedom or to a certain number of nodes. And this is below 100 in some of the softwares. Or if you have it within an in-house code, it can become extremely computationally expensive, and we don't want that. Another approach is to minimize actually the mechanical compliance to make the structure as stiff as possible. For that one, the idea is to not consider the temperature constraints, consider only the mechanical loads, the pressure in that case, and to calculate the optimized design. The downside of that one is that you still need to perform a thermomechanical validation step in the end. Now, the third option is to perform a minimization of the thermomechanical compliance. So there you include also the thermal effects, the heat conduction through the whole material. And that one is not yet commercially available, but that was at least the state of end of last year, 2023. I'm not up to date what happened in the last couple of months, but it was definitely developed within the Great to Excel project by the Ghent University. So if you have any questions about that one, Wim van Papegem is happy to answer your questions. And the last part that you need to set up is the volume constraint. So how much of the volume do we want to remove from the design constraint? Or what's the volume fraction? So let's say you set a volume fraction of 50%, then 50%, and you set this one as the V0 in that formula here, then you end up with 50% of that material is being left at the end of the design optimization or topology optimization. Now then the next one is, well, after you run the first topology optimization, you evaluate it. And for this slide, I want to point your attention first to the part on the bottom right. The green one is what you do collaboratively, and the red one is what, as a FEM expert, you do alone. So when you evaluate the topology optimization results, you look at the design. What is the final design? Here in our case, it created some internal structure, internal ribbed structure. Does it make sense? How can we print it? So you need to talk to the end user with that one. You need to talk to the additive manufacturing expert. Together you sit and you figure out, is it printable or not? If it's not printable, you need to make changes later on. At the same time, how do you want to print that one? How can we print it? So with that one, and then also look at the stresses. Are the stresses well within the limits that the product can experience or not? Now, with all the knowledge that you have gathered there, you then also start to incorporate the additive manufacturing constraints together with the expert for additive manufacturing. What's the printing direction? Where's the base plane? What are the overhang angles? I have to move a little field here. And what is also the minimum wall thickness for the printing? So again, about the minimum feature size that is printable. So you can all include that one in your topology optimization routine. Then once you have included that one, you also update the topology optimization setting. Because for example, you might say that this volume fraction that you have set here, it's not the right one. Let's decrease the volume fraction. Maybe let's choose other convergence criteria, etc. There are a few things that you can play around with. Then you execute the topology optimization again. You evaluate the topology optimization results as well, together, this one again jointly. And then you continue until you have achieved a satisfactory design. And then afterwards, we are at the last step. You need to post-process the results that you got and to prepare it for additive manufacturing. The first thing that is important to do, as you see here by the small dots, It's not, it looks for me like it's dirt on the screen, might be the same for you, but those were little cavities that were created by the topology optimization. Larger cavities here, there, and there, but you need to remove them either or open them up. Otherwise, when you have thermal expansion, it might lead to internal stress development, and that again to cracking due to the air expansion or even air compression after you cool it down. The second part is that you need to do is, together with the additive manufacturing expert and also end user, you need to smoothen the design and also to remove the sharp edges. So as you see here, that was the stress result from my earlier slide. And this is a close-up view, and you see stress concentrations in this area. You don't want that in the final design. First, you don't want to have stress concentrations. And second, you want to also look at what are the minimal printable features. So when you give this result to the additive manufacturing expert, he would ask you why such a sharp edge is needed. This is actually not needed. So you can smoothen it and remove it. And the last step is, you convert the file that you have created via topology optimization that you have post-process, you convert it to an additive, to a file that is readable by your additive manufacturing software, and then you print it. And as a designer, you're done then. Now to sum up, or as a conclusion of my presentation, the first part is that I wanted to show is additive manufacturing is a powerful tool. But when you combine it with topology optimization, you can increase even its power. So that's the first thing that you should keep in mind. The second one is very important that I learned also, especially in the phase of the mono-material solution versus a multi-material solution. Always think first. What is the problem? Do we actually need topology optimization or not? What are the constraints for the topology optimization? And so on. There are many questions that you can already ask yourself before you start. And the answer to those questions, they sometimes help you to avoid some mistakes later on during the work, or they might even guide you into the right direction immediately, and you save a lot of time. The third part is that skilled designers are always being needed. They need to judge the complex designs that are being generated, and they need to be able to work with them. It's not like that the topology optimization just completely eliminates the need for designers. That's the opposite. The next part is, as I try to stress throughout the whole presentation, you need to collaborate. With the collaboration, you can work in an agile manner. You can work together on the specifications. You can define them together. You can evaluate the problem together and the result and iterate quickly until you have arrived at a high quality design that is also printable. And that saves a lot of time. And as you know, time is money. And the last part, which is actually the most important one, is try to divert from the conventional business practice. If you're not open, if you have not done or considered topology optimization at this point yet, but you're still already working with additive manufacturing, with WAAM, with whatever, try to incorporate topology optimization. It might take a while to get used to that one in the beginning, but in the long run, you will not regret it. It's a big step up from the game. And it links also again back to the top one, that additive manufacturing is much more powerful when you incorporate topology optimization. Now with this last slide, I want to wrap up my presentation and thank you for your attention. And this is also again, the slide with our partners. And yeah, I want to thank everyone in this project and all the people that I work together with. And if you have any questions, please, now is the time. Thank you.
Thanks very much, Franz, for the very, very clear step-by-step description of how to get into topology optimization. Thanks a lot. But for the participants, feel free to ask any questions in the chat. In the meantime, I will just prepare the sharing of a couple of final slides. So I don't see any question, which is a good sign. Means the presentation were very comprehensive. So thanks to our two speakers for today. The replay of this webinar will be available in the next days on the Great to Excel website, together with the other webinars that we have been doing the past couple of years. So feel free to connect to the Great to Excel website. On this website, you will also find the list of scientific publications, journal papers, conference papers that have been published during the project. And a last announcement is that we will be holding our final event in the framework of the IIW 2024 conference in Greece between the 7th and 12th of July. So maybe some of you are already planning to attend this big international conference on welding. If that's the case, you will find the Great to Excel partners in the same conference. And we will be holding a dedicated session on the Thursday, 11th of July, on the conference site. And we will be also present there with a booth at the exhibition, and possibly some of the demonstrators that have been built during the project.